Hello, I will talk about special relativity. The increase in mass, suppose the twin brother who goes on a journey in space weighs 100 kilograms on Earth. So when you will move in the spaceship at a speed of 80% of the speed of light, that is 240,000 kilometers per second, according to the mass growth equation of special relativity, the mass in space will be about 167 kilograms, but you will not feel it according to the equation that the mass after the increase in the mass equals to m naught. M naught is the mass at rest, the rest mass, divided by root of 1 minus v squared divided by c squared. Or m, the mass after the increase in mass equals to m naught. M naught is the mass, the mass, the rest mass. That is to say, the mass of the object when it is not moving, divided by root of 1 minus v squared divided by c squared. So in this example, if the mass of the twin that went to the journey in the space to the star epsilon is, if in the Earth it weighs 100 kilogram, so when he is going to the journey in the spaceship that travels in 240,000 kilometers per second, there will be increase in his mass, and the total mass after the increase will be about 167 kilograms. So the mass of the twin that is on the spaceship increased by about 67%. Okay. Okay, now I will talk about the length contraction. As mentioned, the distance from Earth to the planet Epsilon has shrunk from 10 light years to 6 light years only, from the point of view of the twin brother flying in the spaceship. According to the equation of L equals to L naught times root of 1 minus v squared divided by c squared. So L naught is 10 light years, that is the distance between Earth and the star Epsilon, and L is the distance that the brother in the spaceship that is moving in 240,000 kilometers per second, the distance that is measured by him. The distance will be only 6 light years because it shrink from 10 light years to 6 light years, because is moving in very high speed in the space towards the star Epsilon. Okay, but there will be also the length of contraction. It will be also shorter. The height of the twin in the spaceship will be shrinked according to this equation, and actually if on Earth is 8 weighs 1.8 meters or 180 centimeters, then from the point of view of the twin brother who remains on Earth, the height of the twin brother in the spaceship shrinks to only 1.08 meters. So, according to the same equation, we use the same equation. So, as I wrote here, L naught is the height of the twin brother on Earth. Also on Earth, the height of the twin brother is 1.8 meters. And because he is moving in very high speed, his height also will be shrinked. And in the spaceship, his height will be shrinked according to this equation. So L naught is 1.8 meters times root of 1 v squared divided by c squared, so 240,000 kilometers per second divided by 300,000 kilometers per second. That is the speed, the speed of the light will give us 0.8, and all this squared. So in total, we get 1 minus 0.8 squared, and the result is 0.36, and the root of 0.36 is 0.6, and 0.6 times 1.8 will give us the final result of 1.08 meters. So his height will be shorter by 72 centimeters, because he weighs on Earth 1.8 meters, or 180 centimeters, and now he is only 1.08 meters, so his height shrinks by 72 centimeters. So if the twin on Earth had the detector, then the detector would show a height of only 1.08 meters. But the twin brother who is in the spacecraft doesn't feel that he is shorter. Okay? So now I will talk about time dilation. As mentioned, from the point of view of the brother who is on Earth, his twin brother is moving in the spaceship at very high speed. Therefore, the rate of time flow in the spaceship will be slower than the rate of time flow on Earth. While on Earth it took in 25 years for the twin brother to return from a journey in space, but in the spaceship the total time that will pass during all the journey will be only 15 years. While from the point of view of the twin brother who embarked on a spaceship journey towards the Epsilon star, he is at rest and the Epsilon star is moving towards him at a speed of 240,000 kilometers per second. Therefore, in this situation, there will be a contraction of length or contraction of distance according to special relativity. And the total distance between the Earth and the planet Epsilon will be 6 light years only, and the round trip distance is 12 light years because it is back and forth, yes. And at a speed of 80% of the speed of light, the entire journey in a spacecraft will take 15 years due to contraction of distance between the spaceship and the planet Epsilon, as I have already mentioned. But from the point of view of the brother that stays on Earth, because of the fact that his brother travels in the spaceship at very high speed, there will be a time dilation or time lengthening in the spaceship, and the total journey will take him only t equals to t naught times root of 1 minus v squared divided by c squared. As I have already mentioned in the previous lecture, t naught is 25 years. That is the time that is passed on Earth. But because of the fact that in the spaceship the rate of time flow is slower than the rate of time flow on Earth, so there will be a time dilation, or there will be a time dilation, and the total time that it will take, or that it will pass in the spaceship, will be 25 years times root of 1 minus 0.8 squared, and the final result is 15 years, as the brother in the spaceship have already measured the same result. Okay, thank you very much.